In this video, we are going to discuss a problem on circular tank with fixed base based on IS code method. The problem is design a circular tank with fixed base for capacity of 400,000 liters. The depth of water is to be 4 meter, including a freeboard of 0.25 meter. Use M20 concrete and mild steel reinforcement. The tank is free at top and rest on the ground. The first step is dimension of tank. The effective depth of water from capacity of point of view is 4 minus 0.25. The total depth minus the freeboard will give you the effective depth, that is 3.75 meter. If D is the diameter of the tank in meter, then comparing the volume, pi d squared by 4 into height will give you the volume. That means 400, because as we know, in 1 meter cube it can carry 1000 liters. So from that we can find out D, our depth, diameter, which is approximately 11.7 meter. In step 2, we are going to determine the hoop tension and bending moment. So we know that when for a circular tank with fixed base, there will be hoop tension as well as cantilever bending moment. We have to find out the hoop tension as well as the bending moment in this case. Let the thickness of the tank be found out by the empirical relation that we have discussed in the previous video, that is 3h plus 5 centimeter, and that comes as 170 mm. The h squared by dt, from that we are getting it as 8. As per IS 3370 part 4 1967, table 9 and 10. Table 9 will give you the hoop tension and 10 will give you the moment. For fixed base condition, free top and triangular load distribution pattern. Here we are getting the hoop tension at any height represented by Ft is equal to coefficient into Ws d by 2, and bending moment is nothing but coefficient into Ws cube. So Ft is equal to coefficient into 9800, that means the specific weight of water, unit weight of water, and into 4 into 11.7 divided by 2. Therefore we are getting coefficient into 229 320 Newton per meter height. Let that be A. And the moment similarly coefficient into 627 200 Newton meter per height. Let that be B. Why the moment is Wh cube? Because we know the hydrostatic pressure distribution, and the this will be area, moment will be area into the centroidal distance, that will give you mh cube, Wh cube. Okay. From table 9 of 3370 part 4, it is clear that the Ft is maximum. If you are looking onto the table, you can find it, the Ft, that hoop tension is maximum at 0.6 h from top for a s squared by dt value of 8. That is 0.6 h is equal to 2.4 meter from top, or it is 1.6 meter from bottom. The maximum value of Ft is plus 0.575. This is taken from code. We are applying the equation A that we have found out, and then what we are getting is Ft is equal to 0.575 into 229 320, and what we are getting is 131 859 Newton per meter height. The positive sign indicates its tension. That is why it is called hoop tension. If it is coming negative, then it will be hoop compression. Okay. From table 10 of IS 3370 part 4 1967, it is clear that maximum negative moment occurs at 1 h from top, and maximum positive moment at 0.7 h from top for h squared by dt equal to 8. So maximum negative moment, we are getting it as minus 9157 Newton meter per height. That is coming at the base, that means 4 meter from top, and maximum positive moment is coming as 0.0038 into 627 200. What we are getting is 2383 Newton meter per height at 2.8 meter from top. In step 3, so we found out all the hoop tension as well as the bending moment in step 2. In step 3, we are going to design the section for hoop action. Okay, for maximum FT, which is coming at 0.6 H, we have found out it is coming at 0.6 H, that is 1.6 meter from the bottom. The hoop reinforcement ASH, by using the direct tension formula, what we are getting is Ft divided by sigma st. Sigma st we are taking it from table 4 of IS 3370 part 2, and what we are getting ASH as 1146.6 mm squared. Once this ASH is found out, then we have to do the first check, the check for wall thickness. That means the thickness of the wall we have provided based on an empirical relation. We have to see whether it is okay for considering the permissible tensile stress in concrete, whether it is exceeding or not. So here it is 1.2 for M20 concrete, but you have to note that this minimum grade of concrete is specified as M30 from 2009 onwards. Okay, so sigma CT value, we are just checking the tensile stress in concrete by the formula Ft divided by A equivalent area of cross section, that is A plus M minus 1 into ASH. This we have discussed in the previous video, how it is coming and all. And so what we are getting is 0.78, which is less than 1.2, and hence we can say the section is okay. The wall thickness provided is safe. Okay. And as per clause 8.1.1, the hoop reinforcement may be given as a single layer. We can either give it as a single layer, since the thickness of the wall is less than 200 mm. We have provided 170 mm, and so it is less than 200 mm. So the hoop reinforcement can be provided as a single layer, but it is written may be provided. So let's provide ASH in 2 layers in this particular problem. In an earlier problem we have provided it as a single layer. Okay, in this problem let us do it as 2 layers. Therefore, for one layer the ASH value will be 574 mm squared. Let's provide 12 mm dia bars. Then the area of one bar will be 113, and we know the spacing equation A5 divided by area of one bar divided by the total area into 1000, and what we are getting is 196 mm. So after these 2 steps, then we have to go for 2 more check. That is, one check is for minimum reinforcement and the other check is for spacing of reinforcement. The minimum reinforcement criteria as per clause 8.1 of 3370 part 2, we know that it is 0.4% for mild steel bar, and as all the dimensions are less than 15 meter, and the minimum ASH what we are getting is 680 mm squared, and it is far less than 1146 mm squared what we have got, hence it is safe. The checking the spacing of the reinforcement, again in the same clause 8.1.1, the spacing is shall not exceed 300 mm nor the thickness of the section, which is 170 mm. But here we are getting 196 mm using 12 mm dia bars. So if I need to restrict to 170 mm, I have to reduce the diameter of the bar. Okay, so I'm using 10 mm dia bars instead of 12 mm dia bar, and what I am getting is 130 mm spacing. Okay. So hence I am providing 10 mm dia bars at 130 mm center to center from the bottom 1.6 meter of the wall in 2 layers. This is the hoop reinforcement that we are providing for the bottom 1.6 meter, because the hoop is maximum, hoop tension is maximum at 1.6 meter from the bottom. Okay, we can increase while going above this 1.6 meter, we can directly see from the table itself that there is a chance for reducing the hoop reinforcement because the coefficients are getting reduced. Okay, so we can increase the spacing of the hoop reinforcement to the top of the wall section. Let us find the hoop tension for 0.3 H from top. So the table, from the table we are getting the value for 0.3 H, and what we are getting is 76,822 Newton per meter height at 0.3 H. That means 1.2 meter from the top, 1.2 meter from the top. So at 2 sections we have taken this. At 0.3 H and at 0.6 H we got the values. For the 0.6 H we are continuing the same spacing till this much, and here we are trying to increase the spacing because we don't need this much reinforcement over this part, because the hoop tension is getting reduced. Okay, towards the top. So we are trying to reduce the reinforcement or increase the spacing. So the ASH that we are getting is only 668, which is less than 680 mm squared, which is the minimum reinforcement that we have found out in 3B. Okay, so the ASH here is 680, and in this problem we are providing the hoop reinforcement in 2 layers. So in 1 layer it will be 340 mm squared, and providing 10 mm dia bars, the spacing will be 230, and that 230 is greater than 170 mm, which is our minimum spacing criteria 3C, and hence we provide 10 mm dia at 170 mm center to center for the top 1.2 meter height. So here we got 10 mm dia. For this much distance we are providing 10 mm dia at 130 mm center to center, and for this much distance we are providing 10 mm dia at 170 mm center to center. If I am showing the section detail, this looks like this. Okay, we are providing 10 mm at 170 mm center to center for this 1.2 meter height, and for the bottom 2.8 meter height we are providing 10 mm at 130 mm center to center. So up to this much, the vertical wall, we have found out the wall thickness, we have found out the hoop reinforcement at the bottom and top portion. What is remaining is the vertical bar, this one. So the inside vertical bar is provided to resist the cantilever bending action, and the outside vertical bar will be for the distribution reinforcement. So that 2 bars we need to find out. Okay. So the step 4 is the design of the section 4 cantilever action. For M20, so it is cantilever bending. So the reinforcement can be found out by using the formula M that we have studied in the previous video, right? For that we need design constants. This part also is covered in the previous video on design constants as per the working stress design method. For M20 concrete, the sigma CBC value is given as 7 Newton per mm squared. This you can get it from IS 456 table 21, and the M value, it is based on the expression 280 by 3 sigma CBC. Again, this is based on IS 456. What you are getting is 13.3, and the sigma ST value you will get it from table 4 of IS 3370 for AFE 250. Okay. So the design constants are K, J and R in case of working stress method. K is the neutral axis depth factor, J is the lever arm factor, and then R is the factor that we are using in the moment of resistance. So K is M sigma CBC by M sigma CBC plus sigma ST, and J is 1 minus K by 3, R is half sigma CBC K into J. All the details regarding the design constants we have studied previously, so I am moving a little bit fast on that particular area. So maximum negative bending moment, we have found out that it is 9157 Newton meter per height at the bottom portion, at the base portion, right? So the depth equation, we can again check the depth, whether the section wall thickness that we have provided is safe considering the cantilever bending action. We know that m is equal to RBD squared, and d is nothing but root of m divided by RB, and what we are getting is the depth is 83 mm, and what we have provided, the thickness of the wall we have provided is 170 mm, which is far greater than 83 mm, and hence the wall thickness that we have provided is safe for cantilever bending action also. So the area of the steel for cantilever bending, that is the inside vertical reinforcement. So we are using that moment of resistance based on tensile force, that is m is equal to T into lever arm. So sigma st AST into JD, and from that we can get AST is equal to m divided by sigma st JD, and what we are getting is 669 mm squared. Okay. So let us provide 12 mm dia bars. Let us provide 12 mm dia bars, and the spacing of the bar will be again 168 mm. Hence we are providing 12 mm dia bars at 160 mm center to center at the water phase, because it is negative. Okay, that we have seen from our step 2, right? In step 2 we have seen the maximum negative moment is occurring at the base of the tank. So that we have seen from step 2. This is the maximum negative moment. It is minus 199157 Newton meter per height. Okay. So for that we have designed 12 mm dia bars at 160 mm center to center at the water phase. As it is negative, it is coming inside. Okay. This also we have discussed all the bending, how the bending behavior is about the bending behavior and all in the previous video. From table 10, it is clear that this bar is required only for the bottom 0.5 meter height, because once it is going to 0.8 h, the value of the bending moment is turning to be positive rather than negative. So you can see that the negative reinforcement is required only for a depth of around 0.5 meter from the bottom. Okay, so let us provide this for a minimum 1.2 meter height from the bottom, so as to be sufficient for development length also. Development length is 5 sigma st by 4 tau BD. The tau BD, the bond stress you are getting from part 2 of 3370. But I am not going to change the spacing of the vertical reinforcement, because we have seen that the spacing of the reinforcement, minimum spacing is the thickness or 300 mm. Here it is only 170 mm. What we have provided is 12 mm at 160 mm. So if I need to restrict my spacing to 170 mm, what I have to do is I have to reduce my bar diameter and again do that design. The same design that we have done for the hoop reinforcement. So from economical point of view, that is better. You're going for a smaller diameter bar, and you can increase the spacing to the top portion and give the maximum reinforcement at the bottom portion to take the cantilever bending action. So this was again discussed in the introductory video on the behavior of the circular tank with fixed base. Okay, so in that video we discussed all the details. So the maximum positive moment what we are getting from step 2 is 2383 at the outer face. Okay, we have seen again the maximum in step 2. The maximum positive reinforcement, the maximum positive moment is 2383 Newton per meter height at 2.8 meter from the top. At 2.8 meter from the top, this maximum positive bending moment is taking place. So the bending moment will be like this. Okay, it will be like this. The maximum negative at the bottom and maximum positive somewhere over here. Okay, but the value is only 2383. Okay, so for 2383 the AST required is only 174 mm squared, which is far less than 680 by 2. What is 680? It is the minimum reinforcement required, as we have found in 3. And what is by 2 means? By 2 means the distribution reinforcement if I am looking onto the section, this is the reinforcement which is provided for the cantilever bending action, the inside reinforcement. The outside reinforcement is the distribution reinforcement. So whatever the minimum reinforcement required by 2 will give the reinforcement in one layer. Okay, so that is why 680 by 2. So in the outer face I need only 340 mm squared, but what I'm getting from the 2383 Newton meter value is 174 mm squared. So that means my distribution reinforcement will take the positive moment. So going on to step 5, that is distribution reinforcement, and we are providing a minimum reinforcement as calculated in 3b as the distribution reinforcement along the 2 phases. But in the inner phase, the cantilever reinforcement will serve this purpose of distribution reinforcement. Hence, the distribution reinforcement AST at the outer face will be 340 Newton per 340 mm squared, and let us use 8 mm dia bar, and the spacing will become 147 mm. Hence, provide 8 mm dia bars at around 140 mm center to center at the outer face. So the outer face reinforcement, this will be 8 mm dia at 140. After this step, we have found out the entire detail on the vertical walls. We got the section size, section thickness 170 mm. We got the hoop reinforcement at top, that is 10 mm dia at 170 mm center to center, and at the bottom 10 mm dia at 130 center to center. We got the cantilever reinforcement as 12 mm at 160 mm center to center. We got the distribution reinforcement as 8 mm at 140 mm center to center. So what is remaining is the base slab that we are and also the haunches. Haunches means this one. Okay, so we are providing it is customary to provide a haunch of 150 by 150, and the reinforcement also is like 8 mm at 200 mm center to center may be provided. And step 7, it is the base slab. It is very similar to the flexible slab that we have designed, and we are providing 150 mm thickness, and the bars are 8 mm dia at 140 mm center to center. So this is the base slab. So in the haunches we are giving a reinforcement of 8 at 200, and in the base slab we are providing 8 mm at 140 mm center to center, and this is the thickness of the base slab. Okay, this is given over a PCC layer of M10 concrete, and a layer of tar felt is provided in between for a separation between the lean concrete mix and the base slab. Okay, so by this much, this portion is all. Thank you.